Hi everyone, welcome back. How is it possible to build immense structures like the Burj Khalifa, the Millau Viaduct and the nearly 7-kilometre long Gwangan Bridge in South Korea? The answer lies in materials engineering, specifically understanding how materials behave under stress. In this video, we're going to introduce the key ideas you must understand for the materials topic in A-level physics. We'll be covering Hooke's law, the difference between elastic and plastic behaviour, and the fundamental concepts of stress, strain, and the Young Modulus. If you want more videos and online tuition to really master this subject, then follow the links in the description below. Enjoy the video. Before we get stuck into the details of this tutorial, I think it's worth thinking about the context of materials. So I could say a lot about this. I think it's absolutely fascinating. There's whole areas of engineering dedicated to materials, so it's a really interesting area. But just in very simple terms, what you can build depends on the materials you have. Now that might be obvious. So for the last few centuries, or possibly a few thousands of years even, brick has been the main building material, and you can do quite a lot with it. You can kind of do fairly boring bridges and fairly boring buildings. I mean, you might do something quite interesting. If you are a master architect, like the Romans were, then you can build things out of stone and brick, like this enormous aqueduct in Segovia, which I highly recommend visiting, and it will last for 2,000 years. So, but it is quite limited. So it's only when materials develop, when you develop steel and composite fibers and a whole range of reinforced concrete and so on, that's when you can start to build really impressive structures like the Millau Viaduct, which is phenomenal, or the Burj Khalifa, which is just huge. So materials in physics, and in particular in engineering, are hugely important. So we're going to recap the GCSE ideas, which I think are fairly intuitive. So if you get a material, usually a spring, and you hang a force on it, so you've got a weight there, then it's going to stretch, and there's a relationship between the force you apply, called the load, and the amount it stretches, called the extension. And not surprisingly, they are proportional. So this is Hooke's law. So if you double the force, you double the extension, proportional relationship. Now this is only true within the elastic region. So this is really important, and you might have done this at GCSE. You'll definitely do this. You might do a practical in your physics lessons where you get a spring and you plot the data, and there's a straight line section here, and then it starts to curve, and then eventually it will break. And you're probably going to be asked to calculate the gradient of the straight line section. Now in reality, there's a bit more going on here, and we might look at this later on in this particular topic, but not in this video. So in simple terms, we assume that the end of the straight line section, the proportional section, is called the elastic limit. Now in reality, it's not quite the same, but very often that simplification is made. And then it starts to stretch, and this is called the plastic region. So below the elastic limit, if you take this load off, then the spring or the object will go back to its original length with no permanent extension. If you go beyond the elastic limit, then you go into the plastic region, and then at that point, if you take off the load, it will reduce its length, but it will not go back to its original length. It will stay permanently deformed by some amount. So if we have a proportional relationship between F and X, then we have a constant of proportionality, known as the spring constant, sometimes called the force constant, given the symbol K. And if you make K the subject of this formula, K equals F over X, that is how we calculate the spring constant. And we can see here that if I worked out the gradient of this straight line section, then that is going to be F over X, or delta F over delta X. And according to this formula here, that will be the spring constant. So this is really useful. So the gradient of a force extension graph is the spring constant. And this tells us about how difficult it is to stretch a material. It's the amount of force in newtons required to stretch it by 1 meter. So the units of K are newtons per meter. So if you compare different materials, if you have a larger gradient, we say that it's more difficult to extend. It might be a stiffer material, it has a larger K value. And this is quite useful to note that plotting F on the y-axis and X on the x-axis is quite unusual. Normally, because f is the independent variable, we would expect that to be on the x-axis, and the extension should be on the y-axis because that is the dependent variable. However, because for this particular case, the gradient is a spring constant, normally we plot f against x, and then we can compare the gradients directly. Right, so using this, I'm sure you've done this at GCSE, pretty straightforward formula. So this would be a typical GCSE question. You might get an A-level question like this if it was a kind of nice, easy intro to the topic. So if we know the force and we know the extension, we can find the spring constant nice and easy. K equals F over X, 15 over 0.10, or rather 0.1, we need to divide by 100. So make sure that you're in newtons per meter, so extension in meters. You could write newtons per centimeter, but that's not an SI unit and it's not ideal. So normally we work in newtons per meter. And then for part B, what force would be needed to extend it to 12 centimeters? Well, as long as we are still in the elastic region, which we would always have to assume that's the case if we're using F equals Kx, then we just put our value that we had previously, 150, into the formula, multiply it by our new extension, divide by 100, 0.12, and we get 18. Now that should not surprise us because we've increased the extension by 20%, so we should increase the force by the same amount. So 20% of 15 is 3, and we're up to 18. Very important in this whole topic is the calculation of area and also the conversion of units. So you will have done this before, the pi r squared. This is standard GCSE and even Key Stage 3 Year 9 calculations, but it's really important you get this right. Very often you'll be given the diameter, not the radius, and you'll be given the value not in meters, so in this case centimeters. So before we do pi r squared, we need to do two things. We need to divide by 2 to get the radius, we need to divide by 100 to get it in meters, and then we can square the radius and times by pi. And we should expect to get a really small value. So if we're talking about cables or even wires, then we should be looking at 10 to the minus 5, 10 to the minus 6, 10 to the minus 7 meters squared. So expect very small values. The next really important thing we need to consider is conversion of units. So again, you're very used to working in one dimension. So if we're converting centimeters or millimeters into meters, that's pretty straightforward. But if we're in 2 dimensions, so we've got squared, then we need to square the conversion factor. So if I have millimeters squared, well, millimeters into centimeters, that's times by 10. But if it's squared, it's going to be 10 squared. So 1 centimeter squared is 10 millimeters multiplied by 10 millimeters, which is 100 millimeters squared. So that's a conversion of 100. So we need to divide by 100, not by 10. And if we're going millimeters into meters, millimeters squared into meters squared, then the conversion will be 1,000 squared, because 1 meter squared is going to be 1,000 millimeters by 1,000 millimeters, which is 1 million, 1 times 10 to the 6. So we've got this factor of 1 million, so we need to divide by 1 million, which is times 10 to the minus 6. So again, you probably have done this before, but a lot of students forget to do this and they lose easy marks. So yeah, this question 2 and 3 really important. Watch out for the radius, divide by 2, make sure units are in meters, and then watch out for the units of area. It's going to be the conversion in 1 dimension squared in order to make the conversion. Okay, so all of that is GCSE stuff, which hopefully you have done before. So totally new, I imagine, for everyone at A-level is the stress, the strain, and the Young Modulus. Now these are fundamental ideas that if you do take engineering in the future, then you'll look at this in a lot more detail. But the formula you are given in a formula booklet, and they're relatively straightforward. So why do we need them? So if you were looking at a construction project and you had a range of different materials, different metals, and you wanted to compare them, if they were different shapes and sizes, so if you had different lengths and different cross-sectional areas, and then you tested them, hopefully that's obvious that that would not be a fair test. So in order to compare a fair test of different materials, then we have to consider their dimensions, and that can be quite limiting and quite difficult to do. So the purpose of the strain, the stress, and eventually the Young modulus is to take away this issue of different lengths and cross-sectional area. So the first one is the strain. This is given the symbol, the curly E, the epsilon here. That's the ratio of extension to the original length, so X over L. Because it's a ratio, then the units will cancel and we don't get any units, it's just a number. But watch out, very often it's written as a percentage, and we'll look at an example of that on the next page. The stress is given the symbol sigma, as shown here, and that is the ratio of the load to the cross-sectional area. So we have newtons divided by meters squared. You could write that, that's fine, but better than that possibly would be PA for pascals. And you might have seen this before, that's the units of pressure, you might have done that at GCSE. So it's just the same as the units of pressure. And then the final one, the Young modulus, given the symbol capital E, is the ratio of the previous two constants, the stress to strain. So because we have stress in pascals or newtons per meter squared, and then we just divide by something with no units, and the units of Young modulus will also be the same as stress, so pascals or newtons per meter squared. So we're going to practice using these. It's really important you're confident with them with calculations, but you will be given these hopefully, well, you will be given these in the formula booklet. So let's have a look at a worked example. So this would be a nice easy one to start with. So we've got the original length, we've got an extension, and then find the strain. Okay, so as always, write out the formula. This is good practice. Make sure the units are the same. So 4 millimeters is 4 × 10⁻³ meters divided by 3.6 meters. As we can see, the meters will cancel, and we should expect a small number because normally we're talking about a large object with a big length extending by a small amount. So very often we're looking at 10⁻³, 10⁻⁴, maybe 10⁻⁵ for the strain. If we want to convert that to a percentage, we just multiply by 100. In the same way that a half, you know, is 0.5, which is 50%. So 0.5 times by 100 is 50%. Exactly the same here. We multiply by 100 to get a percentage. Question 2 is going to be stress. So we have a force, and we have already given the cross-sectional area, so we don't need to do the pi r squared calculation. So 200 divided by 2.5 10⁻⁵. Be careful here with your calculator. If you're in a bad habit of putting this in as 200 divided by 2.5 and then multiplied by 10⁻⁵, then that will bring this part of the calculation up to the top and you'll get the wrong answer. So you could use brackets, or even better, use the times 10 to the x button on your calculator. Because we're dividing by a very small number, we should get quite a large number. So very often we're looking at megapascals or maybe even gigapascals. You could write, yeah, PA will be better, or newtons per meter squared, if it should get the marks. So the Young modulus, we can use the previous two values, the ratio of stress to strain. So we have 8⁻⁶ divided by a small number, less than 1. So very often the Young modulus will be a large number indeed, usually gigapascals, possibly 100 or 200 gigapascals. So if you're getting 100 or 1,000 or something like that, then you have made a mistake. Okay, so this is your entry-level basic calculation. You've got to be confident with these basic calculations. Okay, so how we would use this, so a couple of things. We could just look at typical values. You're obviously not expected to know these values, but you are expected to work with them. And you could be given a table like this and be asked to compare or select the best material. So we can compare all these different materials directly regardless of their dimensions, because we factored in the stress and the strain, which takes into account cross-sectional area and original length. So this is a direct comparison of how good a particular material is at withstanding a force when it's applied. So basically the strength of the material. And we can see here that steel from this list, 210 gigapascals, is the strongest or most stiff of these materials. Also, we could plot this data, and you may do this as a core practical as part of your course. So you might get a range of stress values and strain values and plot them. And you should notice this looks very similar, almost identical to the one we started off with. which was comparing force against extension. And that should not surprise us, because stress is force divided by a constant value, and strain is extension divided by constant value. So it should have the same shape. We should have this straight line proportional section, and then this curved plastic region over here. Obviously the numbers will be different, but the basic shape will be the same. So we will still have an elastic limit, an elastic region, plastic region, and then at some points the wire or the material will break. We could call this the breaking point, and if we read off the value of stress there, then that will be called the UTS, the ultimate tensile stress. Final point, if I was to work out the gradient of the straight line section, stress divided by strain, we can see that is the Young modulus. So that's a very typical exam question. They might present you with some plotted data and ask you to calculate the Young modulus. Right, good. So that is a bit of a recap of GCSE Hooke's law, and then introduce the new ideas of stress, strain, and Young modulus. So next thing you need to do, so you could go and look at the next video on YouTube. So that would be either the materials playlist, or specifically the one on deformation and work done in energy, polymeric materials. If you want more detailed lessons and structured learning, then you can go to payhip.com, grade A physics. So we've got a lot of these videos, even more videos. We've got quizzes to check your understanding. We've got worked examples, exam questions with worked solutions, exam tips, and progress tracking. So hopefully see you soon. Bye.